Assalamualaikum. Hi. We continue with the Bioreactor Engineering Part 1 on the continuous culture model. So you can refer to the textbook written by Schuler and Cargie, the Bioprocess Engineering Basic Concept, 2nd edition, Prentice Hall, in Chapter 6 and 9. So in the batch culture, growth, product formation and substrate utilization terminate after a certain time interval, meaning that at the end of the fermentation. Whereas the continuous culture, fresh nutrient medium is continually supplied to a well-stirred culture and product cells are simultaneously withdrawn. This product can be withdrawn at certain interval time or it can be withdrawn at the end of the fermentation. So growth and product formation can be maintained for prolonged periods in continuous culture. After a certain period of time, the system will usually reaches a steady state where cell, product and substrate concentration remain constant. This schematic diagram shows the primary types of continuous cultivation devices, which are the chemostat and Torpedo Start. So for the chemostat, it refers to a constant chemical environment and the cellular growth is limited by one essential nutrient and other nutrients are in excess, and this chemostat system requires control elements which is pH and DO as well as temperature. Okay, and the fresh sterile medium is fed and aerated and cell suspension is removed at the same rate. For the Torpedo Start, the cell concentration is kept constant by monitoring optical density of the culture and controlling the feed flow. When turbidity exceeds the set point, the fresh medium will be added. The volume of the culture is kept constant by removing an equal amount of culture fluid. This schematic diagram shows the ideal chemostat. Okay, and here we can see there will be a flow feed in and feed out. Okay, so the substrate and initial cell, meaning that inoculum, will be added up in the reactor. Okay, and then there will be a certain time interval for fermentation, right? Then the product will be withdrawn. So feed out, you might have a remaining substrate or the substrate might be consumed totally during the reaction. Okay, it depends on the reaction itself. And then you will have the value of cell concentration and product. This is the mass balance statement for cell mass. Okay, we have the mass rate of cells into the bioreactor, then minus with the mass rate of cells out of the bioreactor, and then add with the mass rate of cell growth without endogenous metabolism, and minus with the mass rate of cell loss by endogenous metabolism. Okay, which is, we know that this endogenous metabolism, it exists at the stationary phase, okay, and then equivalent to mass rate of cell accumulated in the bioreactor. Then from the previous equation, equation 23, right, you rearrange the equation, then it becomes equation 24. Okay, dx over dt equals to dx naught plus mu g minus kd minus dx. Okay, d here is referring to the dilution rate. You can calculate this dilution rate if you have the flow rate. Okay, then you divide with the volume of the reactor. Alright, then you will have the dilution rate. This volume of the reactor meaning that the working volume during the reaction. At a steady state, dx over dt will be equivalent to 0. Okay. Assume at sterile feed, okay, during the steady state is x naught equals to 0 and kd is small and kd is equals to 0. That can be negligible. Then the cell mass balance equation becomes mass rate of cell out of bioreactor equals to mass rate of cell growth without endogenous metabolism. Okay. Then at steady state, what happens? D will be equivalent to mu, where D is dilution rate, okay, the dilution rate, and D is reciprocal of residence time. Since growth rate is limited by at least one substrate in chemostat, okay, using Monod equation, then we can predict the bioreactor outlet stream of substrate outlet stream. Okay. Then this is the Monod equation, which is at steady state we know that D equivalent to mu. Okay, meaning by using this Monod equation, rearrange the monod so it becomes in terms of substrate. Okay, where we can relate effluent substrate concentration to the dilution rate for D less than mu max. Then next, okay, the material balance on the limiting substrate in the absence of endogenous metabolism, okay, Kd will yield equation 26 here, okay, and you have to note that Qp is equivalent to 1 over x dp dt. This is the product formation, okay, rate, specific rate of extracellular product formation, okay, the product formation rate, right? So for simple case of no product formation, which is Qp will be equivalent to 0, and at steady state ds based on the substrate, okay, ds over dt is equivalent to 0, where there is no endogenous metabolism, and so that Kd will be equivalent to 0. Then what happen is the equation, okay, you will have like the equation 27 here, d s naught minus s equals to mu x over y m xs. At steady state, we know that d will be equivalent to mu, and by solving this x, you will have x equals to y m xs s naught minus s, or you can substitute the terms of s, okay, from the previous slide here, okay, substitute, then you will get this equation number 28. The effect of endogenous metabolism. We know that the endogenous metabolism exists during the stationary phase. Okay. Thus far, the substrate balance equation has been written assuming that y-xs is constant at y-m-xs. Right? With endogenous metabolism, mu g will be equivalent to d plus kd, because there will be an existence of rate of death because of this endogenous metabolism. Okay. So we know that without endogenous metabolism, Kd will be equivalent to 0. But with endogenous metabolism, Kd, we have the value of Kd. That's why the Kd is required, okay, to be considered during this endogenous metabolism. And with no extracellular product formation, the substrate mass balance is at steady state, where based on the substrate, okay, the maintenance coefficient based on substrate will be equivalent to Kd over Ym xs. In the box here, shows you the derivation, okay, of the equation in order to have this final last linear line equation 1 over yap apparent of yxs equals to 1 over ymxs plus ms over d. Okay. Then you can have this type of plot, okay, based on the linear line equation here. Okay, where we know that y axis is 1 over yapxs. 1 over yapxs. And the x-axis is 1 over d. Okay, 1 over d. Okay. Then from this plot, we may able to calculate the value of maintenance coefficient based on substrate. Okay. So that later we can have this Kd value. Okay, because this is for endogenous metabolism. Right. And then you can also have the figure of ymxs based on the interception at y-axis. Okay. The slope of the graph, okay, can be used to calculate the maintenance coefficient for the substrate. Okay. Later, from the equation previously, the previous equation here, ms equals to kd over ymx ms, then you will have the value of kd based on the slope of ms here.